Okay, in this video clip, we're going to do a little bit of a math review. The purpose here is not to actually teach the math involved, but hopefully remind those of you who need a refresher of a few things here. So we're not going to start from first principles or anything like that, but just remind you about a few things, especially with respect to algebra and plotting, that will be useful later on in our course. So certainly if you're doing the more quantitative approach to the course, you'll want to be up on these things. But even if you want to do the more qualitative approach or just taking auditing approach, there'll be times you want to just sort of follow along with the video, and it'll be helpful to remember these certain things. So when we talk about algebra, of course, we use letters, and then we can replace plug in numbers for them. So we have things like this where we say, okay, equations A plus B equals C. So we have two numbers represented by A and B. When we add them together, we get a number C, etc., etc. Remember a few things with exponents. If we have an actual number 2 squared, that is the same as 2 times 2, which is 4, of course, or 2 cubed equals 2 times 2 times 2. Or 4 cubed, 4 times 4 times 4, so it's 2 multiplied 3 times. So we can also talk about something like a squared, certainly a number squared, a cubed. I don't think we really actually get into anything more than squared in here, if I remember correctly. So, but we'll see a lot of squares, a squareds, b squareds, x squared, y squared, things like that. So just remember how that works. Another thing along with this, we have negative exponents. So if we have, say, 3 to the negative 2 power, that's defined to be 1 over 3 squared. Okay, so 1 over 3 squared, 3 to the negative 2, or if we use a to the negative 2 power equals 1 over a squared. Remember also that a to the first power, a to the 1, simply equals a. So a to the negative 1 is the same as 1 over a. We can also, of course, talk about things like the square root of 3, where if you take the square root of 3 times the square root of 3, you'll get 3 back again. So clearly if we have the square root of a times the square root of a, that's going to give us a back again. In exponent notation, we write, instead of using the square root radical sign there, we sometimes write this as a to the 1/2. So a to the 1/2 power is the same as the square root of a. One reason this works is if you do something like this, if you have, let's say 3 again, if we have 3 squared times 3 to the 4th power, what does that equal? You may remember, if you dredge your mathematical memory, if it's been a while here, is that when we have like bases, remember the 3's here are called the bases, and the 2 and the 4 are the exponents. When you have like bases, you just add the exponent. So this becomes 3 to the 2 plus 4, which is the same as 3 to the 6th power. And you can sort of see this because this is 3 times 3 times 3 times 3 times 3 times 3. That's 4 more 3s. So we get 6 3's together multiplied, so we get 3 to the 6th power there. Or in algebraic notation, we might say we've got a squared times a to the 4th, then that's a to the 6th power. Again, if the bases are the same, you can add the exponents and combine them like that. What you can't do is something like this. If you have a squared, some number b to the 4th, there's nothing you can do with that. You can't do 2 plus 4 there and somehow do ab to the 6th or something like that. Because it'd be something like this. It'd be, if you have 3 squared times 7 cubed, you can't just do 21 to the 6th power, 5th power, something like that. Won't work. Doesn't make mathematical sense. Okay, and the reason I just did a reminder over here is, why would we call this a to the 1/2 square root of a? Well, if square root of a times square root of a equals a, back again, square root of 3 times square root of 3 equals 3. If we write this as a to the 1/2, a to the 1/2 times a to the 1/2, bases are the same. These are the same, like bases, so we add the exponents. This becomes a to the 1/2 plus 1/2, which of course is just 1, so we get a to the 1, which is just a. So what we've just shown in different notation, square root of a times square root of a equals a. So that's why we use a to the 1/2, that 1/2 exponent, as a symbol for square root of a, or it's equivalent to the square root of a. So that's a little bit with exponents, a few reminders about that. Some other reminders here that will actually be useful later on. What if we have something like this? If we say a plus b, remember we can factor things out. So we can write this as a times 1 plus b over a. Okay, remember how we did that? Because if we have this, we can get this back because we just go a times 1, so that's going to equal a, and I've got a times b over a. Remember how this works if it's really been a while for you? So this is the same thing as a times b over a, and the a here in the numerator essentially, and the a in the denominator cancel, and we just get a plus b again. So essentially we can factor out an a in this case, or we could have done the similar thing with b. Why is that important? Because we will see later on something like this. We'll have not just a plus b, we'll have a squared plus b squared. That form comes into the theory in a number of cases. And for various reasons, we'll want to write it like this. We'll write this as a squared times 1 plus b squared over a squared. Okay? Because these are equivalent, because I take a squared times 1, that's just a squared times b squared over a squared. The a squareds cancel, I'm just left with b squared. Even though this looks, why would we want to do this when this is simpler? Well, it turns out in certain cases that will give us a nicer form to see what's going on with the math. Okay, so that's factoring something out to just write something in a different form there. Another thing, just as a reminder, if we have a over b plus c over d, so maybe we have something like, what should we do? Just, maybe 2/3 plus 5/2. Okay? Oops, and let me change that. Let's do 5/4 here, just so that A, B, C, and D are all different there. Okay? Obviously, it could be the same, but 2/3 plus 5/4. We want to combine those two fractions together. So remember, we need to get a common denominator. We want the bottom part here to be the same. The way we do that is we do a little trick. We multiply in the form of 1. Remember, so we have 2/3 times, look at the other denominator, the 4. So 4/4, that's just 1. I haven't changed the 2/3. 2/3 times 1 is 1. Plus 5/4 times 3/3, this denominator. And do the multiplication. Remember how we multiply fraction? Just multiply the top, the numerator, and multiply the denominator. So this becomes 8/12 plus 5 times 3 is 15/12. And you can see our little trick gave us the common denominator. So now we can combine those two fractions. It becomes 8 plus 15 over 12. And 8 plus 15 is 23/12, which we could just leave like that, of course, or we could write this equals 1, and because we got 12 in there, and looks like 11/12. 1 and 11/12 is our final answer there. So in the form A over B plus C over D, if you follow the pattern, again, you're going to get AD plus BC all over BD, if you want to just memorize that form. But if you we sort of skip some steps there, but essentially the same thing here. Multiply this by D over D here, and multiply this one by B over B, the other denominator, and that's put it all together and we get that form. So again, basic result from algebra. I think those are the main things we'll need with that. Let's just spend a few minutes talking about plotting points, because later on in the course we'll do some things with space-time diagrams, which can be a very powerful tool for analyzing certain situations. And it's useful, if you haven't plotted things for a long time, it's useful to remind ourselves how we do that. So plotting. And actually, as we go along the course, there may be a few other things that come up that we won't have mentioned here, but we'll mention them along the way as we go, just as reminders of how things work. And I won't try to jump too far ahead. Remember, make haste slowly, as it were. So plotting, remember just how that works. If you've got, we'll use x and y now, some x and y values. So maybe the values for x, often we choose these, maybe -2, -1, 0, 1, 2, 3. And given x, we can find a value for y, or maybe they're just given. Maybe there's some experimental data, and we know the x and y values, and we just want to plot them. In this case, we'll use this. We'll say y is, when x is -2, y is 4, 1, 0, 1, 4, 9. And in fact, you may recognize this as y equals x squared. In other words, take the value of x, square it, and that gives us y. So that's my xy data. And so if I'm going to plot that, here's my x-axis. Here's my y-axis. Put some marks on here. 2, 3, 1, 2, 3, 4. 1, 2, 3, 4. Something like that. So -3, -2, -1, 0, 1, 2, 3, 4. And of course, we could be going this way too. -1, -2, 1, 2, 3, 4, 5, etc., right? And so we plot. So first point, -2, 4. When x is -2, y is 4. So -2, up 4. So there's our point. In fact, let's use red. A little more colorful. -2, 4. We got that. So it's about right there. -1, 1, right? So -1, 1. 0, 0. So point right there. When x is 1, y is 1. X is 1, y is 1. So about right there. When x is 2, y is 4. So again, about right there. And when x is 3, y is 9. So it'd be way up here someplace. And -3 would also be 9, and so on and so forth. And so then we connect the dots. So if we actually plotted a whole bunch of more points, it looks something like that. In other words, we get a parabola from that. We're not going to go into parabolas too much and hyperbolas. Actually, we'll see an example maybe of a hyperbola later on, but we're not going to get that deep into the math. We'll just mention it more or less as an aside as we go along. So plotting points, right? And we often have an equation, y equals x squared. So we choose some x values, we calculate the y values, and we plot our points like that. Now, in particular, I want to do one other type of a plot here that we'll encounter a lot. This form. And this is the form of a line. You may remember the general form. I'll write this up and then we'll explain the details in a minute. So a straight line has the form in terms of y-x form, x and y values. We have y equals, let's call it capital A x plus b. You may see it in slightly different notation, but that's the basic idea. Let's do a simple example. Let's just do, say, y equals 2x. So in this case, A is 2, B is 0. I don't have any B in this case. And so if we were going to plot this, let's choose some values here, x values and y values. Again, we'll just choose some nice values for x. We'll just do, say, -2, -1, 0, 1, 2, 3. perhaps. And so plug this in, negative 2 for x times 2, that's negative 4 for y, negative 2, 0, 2 times 0 is 0, 2 times 1, of course, is 2, 2 times 2 is 4, 3 times 2 is not 9, is 6, and so on and so forth with that. And then we plot it. So we say, okay, here again are axes, y-axis, and the x-axis. And we got some marks here. Try to make them more or less even. So negative 3, negative 2, negative 1, 1, 2, 3, 4, 1, 2, 3, 4, negative 1, negative 2, and so on and so forth. So our points are negative 2, negative 4. So actually I need to go a little bit farther here, down to negative 4. So negative 2 for x, negative 4 for y. Get the red out. Red marker. So there's that one. Negative 1, negative 1, negative 2. So hopefully my scaling is more or less correct here, so we get a nice line out of this. 0. 0 is this point right here. 1, 2, so over 1, up 2. Doing okay. 2, 4, over 2, up 4. Something like that. And then 3, 6, over 3, and up 6 would be up here someplace. And you see if we connect the dots, we get, I don't know if I can do this very well, but we'll try here. Well, not too bad there, a little crooked. But that's essentially the equation of a line. This is a line, 2 times x. And again, if you dredge your mathematical memory, if it's been a while, you may remember this number right here. In other words, a is the slope of the line, the slope. And this is something actually will be important for us to remember. It's not crucially important, but it's useful information in that if we look at this number here, it tells us how steep the line is. The bigger this number in front there, the a value, or 2 in this case, it tells us it's a slope of 2. It has a steepness in a sense of 2. For those of you, again, who remember the exact definition of slope, or for a line at least, it's rise over run. So we measure, the rise over the run here. It goes over 1 for the run and up 2. And obviously, if it went over 1 up 3, it'd be a steeper slope. This would be actually a value 3 here. So the bigger the number here, the steeper the slope of the line. The smaller the number, assuming we were talking about a positive number, the slope of the line would be more like this. If it was 1/2 there, then we'd be seeing something more like a line sort of like that. That'd be a slope of 1/2 if we plugged in new numbers for that and plotted that line. A slope of 1 is going to be at a 45-degree angle, assuming our scaling on each axis is identical. So a slope of 1, if it was just y equals x, plotting 1, 1, when x equals 2, y equals 2, and so on and so forth. And so we get a line right down the center there, right at 45-degree angle, splitting the center of those other two. So that's the slope of a line. One other thing you might say, well, what about b here? What's the deal with b? Well, if you did an example where we did, say, y equals 2x plus 1, okay, instead of doing y equals 2x, we'll do 2x plus 1. So slope will still be 2. The steepness will be 2. What's the 1 mean? Well, you may remember, again, dredging your memory, that it's called the y-intercept. And if you just think about that name a minute, it literally means it's where the line intercepts the y-axis. So here, when y equals just 2x and b equals 0, the line, all three of our lines here, intersected the y-axis, here's the y-axis, at 0. In this case, y equals 2x plus 1. If we changed our numbers here, right, x values would be the same, but now we have new y values because we've changed the equation a little bit. Then we'd find that we'd still have a line of slope 1, but it intercepts the y-axis at, line of slope 2, it intercepts the y-axis at the point y equals 1. So it'd be parallel to my first line here, but intersecting here. So let's see if we can draw that more or less. Well, close. Yeah, there we go, a little bit better perhaps. All right, so the y-intercept would be if we draw a nice big point of intersection there. Maybe we can get by. So 2x plus 1. If it was 2x plus 2, the y-intercept would be here. So it would be a straight line parallel, but intersecting at y equals 2. And then y equals 3, and so on and so forth with that. Okay, so that is the equation of a line, general form A, if it's in y and x terms. Okay, so x and y coordinates. Ax plus b. A is the slope. B is the y-intercept. One other thing we'll think about, what if this was y equals negative 2x here? Okay, let's think about that a minute. So x values would be the same. The y values, though, would change. When x is negative 2, remember we didn't review this in a little math review a minute ago, but a negative number times another negative number gives you a positive number. A negative number times a positive number gives you a negative number. A positive number times a negative number gives you a negative number. Two negative numbers multiplied together, the negatives cancel out, as it were, and gives you a positive number. So in this case, x is negative 2 times a negative 2. That gives me a positive 4. So that actually becomes a plus 4 there. Same thing here. Negative 1 times negative 2 gives me a plus there. 0 times 0 is still 0. But if x is 1, I get negative 2. So that becomes a negative 2. This is a negative 4. That's a negative 6. It just sort of does it the other way around. So when x is negative, now y is positive. When x is positive, now y is negative. And if you actually plotted this, you're going to get something that looks like this. We'll do it like this. And then we're at 1, negative 2. So down here in 2, negative 4. Down there, so something that looks like this. Okay, that is a line with slope equals negative 2. So when we have negative slope, it slopes downwards from left to right. Positive slope slopes upwards from left to right. That will be another thing to remember. It won't be a crucial point if you still are hazy on it, but just something to refresh in your memory bank, as it were. Positive slopes slope upwards. The bigger the number, the steeper it is. Negative slopes slope downward. The bigger the negative number, the steeper the negative slope here. So if it's negative 3, it'd be more steep going that way. If it's negative 1/2, it'd be a less steep line going downward from left to right. Okay, so our picture is getting all messed up here. That's just a quick math review of some of the things we'll encounter as we go along. For some of you, I'm sure that was very, very basic, but for others of you say, oh, wow, I don't remember much of that stuff. So hopefully you're someplace in between there. And there's a nice little refresher here. Again, as we go along, we'll be reminding you about these things, but we won't go into all the detail of the math involved. We'll just assume you have enough math so you can take a more quantitative approach if you like to do that. Again, we really aren't going to do anything more sophisticated than what we've seen here, which is roughly, 9th grade algebra or something like that, depending on how your schooling system works. So maybe middle school type of thing. Okay, so that's a quick math review. That actually concludes our set of introductory video clips. And so in the next set, we can get on to our week 1 material where we learn more about physics circa 1900. We see some new Einstein quotes to ponder. We learn about physics circa 1900. We learn about Einstein circa 1900 as well.